Good afternoon and welcome to this webinar provided by bobwillis.co.uk. So just a little bit about my background before we start talking about our subject today, which is microsectioning. I spent my career being a mechanical engineer by profession. I've worked in printed circuit board manufacture, the assembly of printed circuit boards. I've worked in failure analysis. I've worked in quality control positions, and of course also in contract manufacturing. And over the last 40 years, I've run training and consultancy projects worldwide and also run training courses for many of the organizations, again, worldwide. More recently, over the last sort of 10 years, I've presented online webinars, which has obviously become even more popular over the last 2 years. So that's a little bit about my background, where I've been involved, and you can read more of this when you receive the slides on my bio. In addition, there is some more material which relates to the subject we're talking about, but also on general PCB failures, assembly failures on my YouTube channel. And there's lots of material on there about books that I've reviewed, also projects that I've undertaken, and there's about 60 or so defect of the month videos which explain how a defect happens, but more commonly shows you how it happens. So it gives you a better understanding of what you might see occasionally in manufacture. So on to our topic today, which is microsectioning. Now, we will talk about microsectioning of printed circuit boards as a quality control technique for boards. However, microsectioning can be used in a variety of different applications, and particularly when we're talking about the assembly of printed circuit boards. And there is the standard method of making a microsection, but there is also some variations that you need to consider depending on what you're actually trying to cut up and examine. But first of all, books on the subject. Well, if we took a look at books on PCB fabrication, I show you a range of different books here, and some of these are in fact free of charge. You can do a search online and you can find them available as a download. The classic book about printed circuit boards is the Printed Circuit Handbook, written by Clyde Coombs and Clyde Coombs Jr., and then more recently edited or assisted the editing by Happy Holder. So that's the classic reference book, and it's probably about time there's a new one out. That's probably about 6 years old now, but it really is a doorstop, so an incredible reference source for PCB fabrication. Now, in terms of test methods and also test criteria, two publications you should be aware of, you may well already be aware of, is the IPC 600, and this is the acceptability of printed circuit boards. Remember that I said that the majority of microsections that are produced today are for printed circuit board assessment, quality, failure analysis, etc. And this gives you a guideline on what the criteria is based on what you have requested from your PCB manufacturer. And you will have defined what you want, and there within that document there will be basic optical visual criteria based on that. The test methods manual is a manual, as its name suggests, but it's all of the test methods that are covered or included in documents within IPC. So there's a test method for pretty much anything, but there's specifically one on microsectioning. Another classic book that I'd like to mention is a gentleman called Preben Lund. He was a quality manager for many, many years in different European manufacturing facilities and then became a consultant. And it still is a classic book showing you about microsectioning, how to produce sections, and also the general quality control. You'll probably find this online somewhere, or even a library book, etc. But again, another classic book on the subject. Now, first of all, the test method and test method manual. Now, the test methods manual is something which is online, and the actual individual test techniques, if you like, or sections have been available free If you buy the whole book, then you pay for that, and it's pretty big, and you really wouldn't want to spend too long trying to download individual documents if you wanted the whole book. It's much easier buying the whole thing from IPC. But there is a specific section on manual and semi-automatic microsection production. And again, it's written by people that have produced microsections, and hopefully that is another useful guideline. Just do a search for this particular document when you get the reference number when I send out a copy of the slides. Now, in addition, there is an IPC document, 9241, which again is detailed or detailing the methodology for microsectioning. And this includes other things other than just PCBs, but again, primarily it's PCB related. Now, within the document, it goes into how to cut out samples, how to prepare the samples, how to pop the samples, and then various other steps that we'll go through in our presentation. And it also is very useful and helpful because it highlights some of the variations that can occur if you're not careful when you're preparing the samples. And of course, if you don't prepare the samples accurately, then you get misleading information, and that then could be embarrassing if you complain to a particular supplier that you haven't got what you pay for, however it's due to how you've examined the part. So again, reference there is very useful. In addition, it shows you some of the reasons why certain defects within microsections happen. So if you're preparing a sample and perhaps you haven't done it the right way, what things you might expect to see and the possible causes of those imperfections when you're looking at samples. I don't profess to be an expert in producing microsections. I've done it for many, many, many years, but there's a lot of people out there that are a lot better at it than me. Perhaps they have more patience than me. So if we talk about, board related issues to start off with, or boards in general, then you will specify a printed circuit board, or you'll source a board, or you'll be evaluating a board for a customer based on a standard, a document, and of course the design that you have had produced from the supplier. Now within that you will specify certain things. You'll specify the size of things, the thickness of things, the plated layers, etc. And all of these things can be examined using a microsectioning technique. The one thing to bear in mind is obviously with microsection, you're cutting the board up. So it's a destructive technique. However, there is lots of information that can be gathered when you're examining sections. And hopefully, in most instances, if you do it correctly, then you'll be able to get to the root cause of the problem. Now, traditional microsectioning has limitations, and there are other techniques that you can use that go another step forward. So you can take a microsection, which if you're doing it yourself, that's fine. If you're having it done for you, may cost you 200 euros. You can then spend a lot more money re-grinding, re-cutting that sample to get a lot more data and a lot more information. And that can go into the thousands of euros. It just depends what you want from that investigation. Now, within the IPC 600, you've got pictorial images and you've also got photographic images. And within each of those, there is criteria based on the class system, class 1, class 2, class 3. Class 1 being for consumer electronics, toys, etc. Class 2 for telecommunications, for some automotive products, and class 3 being the highest level. So again, there is an image, but remember the images are representative examples of. They're not necessarily specific criteria. The wording within the document is the most important thing you must always follow. So when you look and see something which is got multiple defects on an image, it is the text which is the thing you follow, not just the pictures, because it's difficult for many people to get lots of different color pictures to suit the documentation, as you might imagine. However, they are a good source of reference, they are a pictorial guide, and sometimes, as I always say, a picture is worth 1,000 words, but it is the words which are the legal requirement or the contractual requirement from you to your supplier and your supplier back to you. So in the example I show you here, you've got cracks in the copper, which may or may not be after some form of thermal cycling or thermal shock. So you might have tested the board to see whether it actually will live up to the standard that you require, and you're doing a before and after image or a before and after microsection to look at the robustness of that assembly. Microsections can be done and can be used on more advanced boards, and here we see an example of buried blind vias and filled vias. So we've got vias which are actually plated up with copper, and we can look at the interfaces, the connection points, and assess whether they meet the requirements that you have within your documentation. Now, in addition to the slides that I'll be sending you after the end of the webinar, I've also got a set of wall charts, and these are just typical examples of defects. So there's a set of wall charts as a PDF, so it's just an extra thing I'm sending you as part of this webinar this afternoon. Again, you can print these out, you can use these for use within your own organization. They're not for circulation outside of your organization. So let's start to talk about our subject. Well, if you take a printed circuit board or a printed circuit board assembly, the important thing is deciding on where you want to examine. So we're defining the specimen or the area. And the key thing when you're cutting up a sample, whatever technique you use, you don't want to damage the area of interest. So if you're removing components, sometimes it's better to do it mechanically rather than desolder it, because you're putting heat into the board. So you might actually modify what you're trying to examine by heating it. Equally, if you cut it up inappropriately, you might damage and actually introduce defects into what you're examining. So the key thing always is to make sure you're separating the board way away from the area of interest, and you want a technique that minimizes the possibility of any damage to that area. So you might be using a grinding wheel, you might be using a circular saw as shown in the photograph, or you might be using another technique. There are lots of techniques out there. So we're getting the sample ready, and because we're removing the sample, cutting the sample away from the area of interest, there'll obviously be something we might need to remove before we actually go into the specimen encapsulation stage. But I'll highlight that and illustrate that a little bit later on. So the next step obviously is encapsulation, and there are different materials that you can use to encapsulate your sample. And what you're actually doing is locking the sample in, you're preventing anything moving, you're allowing the edges to be supported during the grinding operation. So again, you're minimizing the surface damage that might occur around the sample you're trying to look at. The next step is grinding, and we use basically wet and dry paper, the similar sort of paper that you use when you're perhaps getting blemishes out of paintwork on a car or on a bike, a scooter or whatever, before a painting operation. And we're using different levels of paper. We're using water to lubricate that paper, but also to take away any residue from the sample. We then go into a polishing phase, and the polishing is basically taking out the scratches you've put in by previous operations, as you'll see a bit later on. And when you get to a certain level of quality that you're happy with, that shows what you want to show, we might go into an etching stage. Now, etching is you're using a chemical to enhance the surfaces you're looking at, or to help separate the surfaces. Because if you've got multiple copper plating strikes on a sample, it might be difficult to differentiate between the colors. If it's nickel, let's say, on copper, it's very obvious. There is a dividing line between the two. So sometimes the etching is done for those reasons. Sometimes it's to enhance certain areas of the material, like for solder, for instance. Certain solders, depending on the etching process you use, will show up different facets or different alloys within the plating. And then, of course, we go on to the inspection stage. So that's the basic process that we go through. So if you look at this example, this is manual grinding. And you can see an unskilled operator, myself, back in my youth, holding a microsection, and I'm holding it on both sides, and I'm applying pressure with my forefinger on the top. When you're doing it manually, what you're trying to do is keep a flat sample, a flat face, but you might be trying to take a little bit more material off the back or the front to even up the sample, to get to the area of interest. And that's why you're holding in this sort of way, and you're applying pressure possibly on the front or the back or the middle, depending on where you are in the sample. Of course, if you're doing this automatically, then this is sometimes taken care for you. But I would always recommend doing microsections manually to start off with. That's how you learn to do and use these techniques, and then you can let the equipment take the strain at a later stage. Now, after you've got to a certain area, then you'll go on and change the paper, and we'll talk about that in a moment. But on the right-hand side view, I'm just showing two different techniques of manual grinding. One that I've just been mentioning on the left-hand side is where we've got a rotary table. We've got water dribbling onto the sample to wash away the debris, but also to keep the sample cool. Otherwise, it overheats, which you don't want that to happen. On the right-hand side, you're seeing a truly very boring manual method. And what we've got here is, again, wet and dry paper. You've got water, which is just dribbling down like a little waterfall, and you're going up and down, up and down, up and down on the paper. So you don't actually have a rotary table to grind off the sample. You're doing it all manually. So yeah, those techniques still exist and people still use them today. I would like to try and avoid it, but that's where I used to do samples when I very first started. So that's sort of the basic technique. Now, there are 3 suppliers in UK and Europe who supply all of the materials, all of the equipment, and variations in between. And each one of these suppliers provide both expertise on microsectioning for different applications, as well as in some cases workshops, practical hands-on workshops. I worked with Struers once doing a workshop in Chelmsford, where I live. But each of the suppliers offer that type of expertise and support if you want it, as well, of course, as supplying all the material and the equipment. So again, I've included the 3 most popular. So again, you can get further material from them. And again, 2 of them are worldwide suppliers as well. So just an example of an automated system. And what you're looking at here again is a rotary table. You've got a plate which holds the sections, which we'll see in a little bit more detail later on, in position. You've got a post which comes down and applies a specific force onto the top of the section. And again, you have automatic feed of the different materials, the different chemicals to the surface, and all you need to do possibly is just change from grinding papers to polishing papers, or you may have a separate system for polishing. And these systems are so sophisticated that they can take off a certain level or a certain amount of material from your section. So they're actually doing measurements as well. Again, the sophistication is amazing nowadays as opposed to when I very first started doing microsections. Again, just a close-up, just showing part of the polishing stage, and you can see the polishing fluid being dropped onto the table, and the yellowy white microsections being held in the rotary tray. So what you want to do when you're cutting a sample out is introduce the minimum possible damage to the sample. So you'll find that a lot of companies will use rotary diamond saws, and this is just an example of one. Again, with this, you would introduce some method of cooling, i.e. liquid cooling, to minimize the possibility of damage to the sample. But even with this technique, you would still cut away from the sample. You wouldn't cut close to the line of area of interest, be it a solder joint, plated through holes on a PCB, or some other area that you're particularly looking at. You're always working away from the sample to start off with. So if we take a practical example, so this is an area array package. Most of you will be familiar with a BGA, an area array type package, and you can do a cross section which goes along one row of balls, and then you could then subsequently microsection the next row, the next row, and next row. So if this was being done for you by a supplier, he would charge you X amount for producing a microsection, which would be the one row of balls. If you then wanted to examine the next row or the next row or the next row, he would charge you more because he's having to re-grind and re-prepare each level. So it's not €200 and you get all the balls on the package. It's one row and then you pay a little bit more. Obviously, you're down to negotiation how much that might be. Another way of looking at it is doing a cross-section from the corners, as you see in sample C. And that can be useful sometimes because you can see balls in different rows, but you can see it in one microsection. So it's more cost effective perhaps, but you can also measure the warpage, distortion of the package and board during the soldering operation possibly, and you can look for other facets of interest just with one hit. So it's more cost effective possibly, and you're getting more information for the expenditure. And it's just a different technique, if you like. And you can see here, this is a microsection that's been taken like that. So you're looking from corner to corner rather than across the edges. It very much depends on what you are looking for when you're doing this. Now, I mentioned that when you're doing a microsection, whatever it might be, you're cutting the sample out from the master board, the panel, the PCB assembly, etc. And then slowly what you want to do is get closer to the area of interest. And rather than potting it and then taking a long time to get to that area, what you do is you grind the sample closer to the area of interest because you're not having to remove so much material. So you're just removing parts of the printed circuit board as opposed to the circuit board plus the molding compound. And this is the sort of stuff that I would do and do all the time. So what you're looking at here is just us grinding closer to those three solder joints. So you can see we're probably 4 millimeters, 3 millimeters away, but we're just getting closer to, and because you're grinding less material, it'll be quicker to do. And of course you can accommodate any movement. So if you are going to grind through 4 or 5 millimeters of printed circuit board in an epoxy section, it's always the possibility of you're not going to be flat afterwards. If you get much closer to the sample, you haven't got to grind as far, so you're less likely to wander off at an angle. But again, it's your own experience, it's your own practice. So you can just see I'm using a grinding paper, we've got water lubricating the surface, and I'm just slowly grinding down till I'm closer to the area of interest. Now, with potting a microsection, there are different techniques that you can use. And I just thought I'd include some of my old potting frames, if you like. And what they are is basically they're stainless steel. There's big holes in them, which is where the epoxy is going to go. There's a back plate. So in the photograph on the right-hand side, you can see the back plate. They're tooled. They've got dowel holes in them and dowels. so they link together, and these would be lubricated first of all. So basically you put on a lubricant onto the surface which is compatible, which is basically just a grease, to allow the sections to come out nice and easily when you have allowed the epoxy to cure. You don't want to be bashing them out and possibly damaging the section. You want them to come out nice and easily. But if you forget to lubricate them, quite often they may well be trapped in there, and you have to use a minimum amount of force to force them out. So just a close-up view, because most of these were being used for microsectioning techniques, you can see a V-groove. So on the close-up on the bottom right, I show V-groove, and when we took a sample out of boards, they would always be a defined dimension out of the board based on the techniques we were using. So they would literally sit in these grooves. There is nothing worse than putting a sample into resin, going away while it's curing, and find the sample has moved, because you've got to start all over again. In fact, it's very difficult to recover the situation, or very time consuming to recover the situation. So you don't want the sample to move. It's extremely frustrating. But this is just one technique. You can buy, and they're available from the suppliers I mentioned earlier, molds like this of different sizes, because obviously you get different size samples you might want to cut up and examine. And these have, again, got a top and a bottom. Again, I would still grease these. We're not talking about putting on a thick layer of grease on. It's literally just a thin layer to allow them to separate out after the curing operation. One of the benefits of this type of plastic mold is, if you have a problem, if you forget to lubricate the surface, you can always use a hacksaw to cut the plastic off and then get the epoxy out. But everybody will know what you have forgotten to do if you do this in a laboratory. So if you remember the basics, you shouldn't go far wrong. Now, we still need a method for holding up the sample. So here you've got one of these molds, but you've also got a little clip to hold your sample in position. And there's a variety of these different clips available depending on the suppliers you're working with. And the one on the left-hand side, literally you just plug your PCB or your sample into there, push it flat so it's sitting flat on the base. The other two examples are slightly different designs, but you've got standoff lugs as well. So it's stood off the printed circuit board, so it's stood off the base of the molding container. And then obviously you've got a position where you can put 3 samples in as opposed to 1 sample in. Again, there's loads and loads of these different things available in the marketplace. And some of them are specifically designed and tooled so you can do multiple microsections preparation in one operation. So there's lots of different facets for this. I mean, generally speaking, all of the microsections I have ever produced have just been, the one-offs, apart from when I worked in printed circuit board fabrication in my youth many, many years ago. But again, all we're trying to do is hold it still, hold it upright. So we've got our sample, whatever it might be. We've cut it out. We've ground it to the area of interest. We've put it into some tool, some piece of plastic clip to locate it so it's not going to move during the curing operation. So here we've got a sample. We've put it into the mold, just make sure it's sitting there nice and comfortably and flat. And now we're ready for adding the epoxy resin. So in this particular case, what we're doing is pouring in the resin. Now, you will know from your own experience how much resin you need for one pot. So again, you would tend to prepare, let's say, enough for 3 or 4 sections, however many, based on what you know the volume is for that particular pot. Now, a couple of things here. First of all, resin systems, they're available from different suppliers. You've got materials which cure very, very quickly. You've got materials that cure overnight. The materials I used to use would cure within about an hour and a half. So there were 2-part epoxy. So you've got the hardener and we've got the epoxy resin. And what I personally used to do, in line with allowances from the supplier, I guess, was I would maintain the resin at an elevated temperature, so above ambient. So it would probably be about 30 degrees or so. The reason for that is that when I mixed it, it was more fluid, it would penetrate much easier. Any small bubbles that were present within the epoxy, they would quickly rise up and escape through the material. What you're trying to do is make sure the epoxy resin gets into the sample, around the hole, in the via hole. You're not left with a bubble. You're not left with a gap. Because if you get a gap, then that might affect your cleaning and polishing operation a little bit later on. So any cavity you want to try and fill, all right? Any cavity you want to fill. If it's just a printed circuit board with some chip components on, a printed circuit board with solder joints on, then that's fine. But if it's something that's got a cavity in, ideally you want to fill it first. So as an example, if you were microsectioning a board which got an electrolytic capacitor on, it would be better if you could remove the capacitor body without destroying the solder joints. If it's a switch, if it's some sort of inductor, if you could take away whatever material, or if it's a switch, you might fill the switch as well. The reason being, you're not left with a cavity which is going to collect resin, it's going to collect other contaminants that you're going to produce during the microsectioning technique. So again, it's preparing for issues that might occur. Now you can put this sample into a vacuum and pull a vacuum, i.e. suck out all the voids or suck out all the air. But I never used to do that. I preferred to have the material at a higher temperature, storage ready to run, add in the curing, the hardener, and then go from there. And it always worked very successfully for me. But you can vacuum out if you want to. That's an option with doing microsectioning. So again, we put the epoxy in there. We're going to leave it in an oven an hour, 2 hours, and then that sample will be fully cured, and I'll be able to move on to the next stage. So with microsectioning, the next step is you can either do it as I was trained manually, which I wouldn't recommend, it's extremely boring, or you're using rotary tables. So the rotary tables I'm showing here on the left-hand side are basically, it's a table, it's rotating. You're dribbling water onto the surface to wash away the residue and also keep the temperature low. You've got papers of a certain grit. So you're buying papers which are of different specifications, and depending on the numbers on those pieces of paper, the amount of material that would be removed. So if you had something that was 100 grit as opposed to 400, the 100 would take off more material and leave deeper scratches in your sample than a 400. So you generally start off grinding with papers between 200 to 400 and then progress up to 600, 800, and so on before you move on to a polishing operation. Remembering that the higher number is going to take off less material. So that's part of the reason why you want to get close to where you want to be prior to potting, and then you take it that little stage further when you've potted it, but still be in control to get the perfect microsection that you want. So this graph just illustrates some of the numbers that I was talking about. And this is the silicon carbide on the paper. As you see here, the numbers represent a degree of aggression, how much material is being taken off. Again, different suppliers use different graphs to illustrate this particular example. So if you see this company, MetPrep, you can see here they've given you the average size of the grit, and also they've given you an indication of the number it relates to. So again, it gives you a feel for what you might be using for your samples. But typically, as I said, I'd start off at 400, maybe 320, and then go on from there. But certainly the 320, 400 would be taking off a lot of material from my section prior to going on to the next step. And whenever you're grinding a sample, you are grinding, first of all, in one direction, and then you're rotating the sample, as you'll see me do in a moment, in the other direction. And what we're trying to do is remove the scratches we put in with the first. It sounds a bit weird to say we're taking out imperfections, but in reality, that's what we're doing. So we put scratches or grooves in the surface as we're removing material, and then we rotate the sample to improve it on the next. But obviously, you're adding scratches again on the sample. Okay, so here's an example of the unskilled operator, me, but been doing it for a long time. And I'm holding the sample, the table's rotating, and you can see me just rotating the sample. Okay, so I'm doing that all the time in between looking at the sample to see where I am. So if it's a plated through hole, I'm trying to get to a certain position. If it's a solder joint, I'm trying to get to a specific position. And ideally, I'm trying to control that right across the length of the microsection, because if you're going to be cutting up, 20 joints, you want to see all 20 joints with the same depth of grinding. You don't want some that are bigger than others. You want to control that. And you can do it with time and care manually. You can do it more easily automatically, but with both techniques, you can screw up if you don't do it properly. So again, the actual amount of water you're applying, this is just in a grinding operation. It's very dependent on what you're removing, but really it's just not much more than a dribble, but it's doing those two things. It's removing the debris, and again, it's maintaining the temperature of the sample. If you try and grind without any water, lubricant, then you're going to feel the temperature rise quite quickly. The next thing you must do is whenever you're moving to the next step, i.e. moving to a different grinding paper, or going from grinding to polishing and then polishing to another level of polishing, you must wash the sample. And please wash it thoroughly, because if you move on to another step and there is debris from the previous operation, all you're going to be doing is messing up what you've previously done. You've been adding debris, which will add grooves and scratches to your microsections. So always wash between each step, each stage, each paper, each polishing stage, just to minimize the possibility of any damage you're introducing to your sample. And as I previously said, rotate the sample, and I'm just using my forefinger here, as you see on the lead, just to apply a little bit of pressure. But I'm applying the pressure at a position to allow me to grind the sample, but also to even out. So if I've gone a little bit too far, then I can compensate by applying pressure at one position or another to get all the microsection or the joints or the through holes in line again to recover the sample. Okay, so that's the grinding operation, and let's look at a sample. So first of all, what I'm showing you here is just a sample of a plated through hole that's been soldered, one that the solder hasn't filled completely. And all we're interested here is just making sure that we've got close to the center. So you want to end up on the center line when you've finished your polishing operation. So you're grinding, getting close to the area of interest, and then what you've got to judge is the level you go, the distance you go before you introduce the polishing operations to make the sample the best you can do. And the key thing is, if you go too far or you don't go far enough into a microsection, you're not in the right plane to do repeatable, consistent measurement. Because if you go too far or don't go too far into the sample, then the measurements you make of copper plating thicknesses or whatever may be inaccurate. On plated through holes, it won't be inaccurate on the track thicknesses, etc., or the copper weights on a board, but it will have effect on the plating in the plated through hole because it's a round surface. I don't need to explain that, I'm sure. So, just to clarify, here's our microsection, and just one thing while I'm mentioning it, if you are going to do microsections on via holes, where the via hole, the through via is capped with solder mask, etc., it's important to break the solder mask. So I would normally always just take a pin and prick the solder mask to make sure the epoxy resin I'm going to introduce is going to go into that via. The reason being, if you've got a plated through hole you're examining and you don't support it internally, when you're grinding the sample, what will tend to happen is you'll damage the sidewalls of the plating, and then any assessment you make on the quality of the board will not be true because you've damaged the board. It's not as it was received. So where there is solder mask over vias, try and see if you can fill the hole. That will improve the performance of your microsection. But typically speaking, it's going to be an open hole. The key thing is to find that center line, cut through to the center line, and there's your accurate area for measurement of plating and plating thicknesses. If it's off, as I'm sure you can interpret here, that you would get a thicker deposit. So your copper would appear to be thicker. I've obviously exaggerated. I don't believe that when you're doing a microsection you're going to go as far as this. But if you are off, there is the possibility of inaccuracies during the measurement cycle. So again, in the IPC documentation, it gives you some indications of accuracy or inaccuracy based on position, and also if the sample is at an angle as well. So I mean, you're trying to keep the sample straight, as I've illustrated to you. I've shown you a few techniques, and also I've highlighted to you what can happen if you are not in that center position. So we've gone as close as we possibly can to the point of the area of interest. We're going to wash the sample again and then go on to the polishing stage. So the polishing stage again uses a material, and we're using a polishing compound. Again, lots of different materials available from different suppliers. Review them, talk to them, find out what's appropriate for your particular application. But this is an example of a semi-automatic polishing machine, and all we're doing here is we're mounting the sample. There was only one on this wheel here that you're seeing. We're introducing the polishing compound, and we're leaving it on there for 2 or 3 minutes perhaps. It just depends on the material and the combination of materials you're using on the polishing wheel itself. In the old days, one of the ways I was trained was to take a piece of silk, so silk cloth, place it on glass, a sheet of glass, and use the material, so the brasso material, the thing that you'd use to clean up brass. And that's literally how I was taught originally to do microsection preparation. That was from a metallurgist by profession. So he knew what he was doing. Obviously, he would have liked our modern techniques. And the idea of the silk was very flat. It wouldn't just trying to think. I'm trying to think of the word. It wouldn't put corners on surfaces. You still get a nice flat surface because you're actually you were actually polishing on glass, but the silk was just holding the polishing material in place. So that was the reason for using that. But probably most of you that are on the session this afternoon won't be doing it like that. But that's a technique that can be used and worked perfectly well during my younger years. Now, the next step is etching. Remember I said that when you look at a sample, particularly if you've got lots of materials which are the same color, like copper on copper on copper, or some solders, like some lead-free solders, it's difficult. All they look, because the majority of it's tin, they just look like tin. They look white in color. So each different metallurgist has little, I guess, formulas for his own etching compound. So I've listed some here, which is taken out the IPC standard. So again, you produce these specifically for etching different materials. And again, if you are working with a PCB manufacturer, he will have his own technique for looking at microsections, and he will probably recommend to you what you do. So when you've got an etching compound that you use, you're cleaning the sample first of all, you're putting it into the etching compound, but it's only in there for a couple of seconds, 2 or 3 seconds. It's out, you wash it in clean water, preferably warm water, and then that stops the etching operation, because you can over etch a sample and you will certainly see the grooves, the differences, but they will be exaggerated because remember, it's etching away metal to show you the differences in those surfaces. So you're only really etching for a few seconds to get the result that you actually want. Okay, so let's look at some practical examples of PCBs. And what I've done here is I've just sort of taken some samples and highlighted the bits, if you like. So we've got microsection through tin lead plating on a PCB, and that white and black surface, that's what you're seeing. So after the etching operation, you're seeing that. If you were to do this without etching, you may well not see the black so vividly within the tin finish. And then the next layers of copper. So we've got the original copper foil, which is the bottom I'm pointing to, and you can actually see there's lines in the copper foil. When it's actually produced and plated, you get this effect in the foil itself. That's based on the way it's plated. The next 2 layers, you've got a strike plate, basically a thin layer of copper, which makes the interconnection from the top to the bottom of the board, so it's making that interconnection. And this is normally electroless, so it's not you're not using an electrical connection to have this plating operation. It's electroless. And then the next step is electroplate. So when you've created an electrical connection between the whole of the board and the sample and the liquid you're going to be adding to it in the PCB manufacturing process, then you'll plate up. So you've got a thin layer. It's probably about 1 to 2 microns. And then you would have extra thicknesses up to around 25, 30 microns of copper to give you that reliable copper plating. So that's, a typical example. Next example is a sideways view, and I show you tin lead again. The reason I show you these tin lead samples is it's nice because you see how changes take place in plating and etching operations in a PCB fab more than you would to do today. Because if you're using just tin as an etch resist over the surface of the copper, you wouldn't see it as obvious as this because of the thickness of the plating. The other reason for the plating thickness, this is the tin lead plating thickness, is when we used to do this for boards, the tin lead became the solderable finish. So some of younger engineers may have heard the term electroplated reflow or tin lead reflow as it relates to board manufacture. Well, it's tin lead plated, and then we reflowed it to make it solder, because a reflowed tin lead plating would have a longer shelf life than just a plated finish. That's why you see the structure. And again, you can see the foil and you see the plated layers. In this example, this is a microsection, and you can see the copper in a multi-layer printed circuit board. And I just pointed out the solder, the copper plate, and the through interconnection within the board, making connection with the through plating. Just a couple of examples. And here we've got vias, buried vias, and blind vias. A buried via is a plated through hole in a board. So that's what a buried via is. But a buried via or a blind via, as is indicated with the top arrow, again, you can see the hole, but you can't see the bottom of the hole. But with a microsection, obviously you can see the interconnection from the bottom of the via to the plating inside the printed circuit board. Again, these are all sort of common things that you'll see in a printed circuit board today. Now, microsectioning, you've got to do it properly. If you don't do it properly, you're not going to see anything. I wanted to share this example. I was doing some work with a company when I was doing temperature cycling on boards. This was during the introduction of lead-free technology. So we were making boards. We were producing 0.2 vias, which was high-end at that time. And we wanted to see the reliability after temperature cycling. So these were microsections. They were produced for me. Now, they don't show me anything. They are awful. So I took the sections and re-prepped them. I did them again. So I grinded them slightly, and then I polished them and then etched them. And I'm not saying, like I said earlier, I'm not perfect, but I'm a lot better than this. So in these two examples, you can see some solder in a hole, and on the right-hand side, you can see a milky white deposit. That's about as best you can see. So after re-preparation, so taking the samples, just re-prepping them, this is what we've got. So on the left-hand side, I can see the effect of my temperature cycling. So you can see in the center area where there's a little crack where the copper is separating slightly, that would not fail. So even if it went on to 2,000 cycles, it honestly wouldn't fail. I mean, my experience tells me that. But it's evidence that something has happened. If you don't see any change after temperature cycling for 1,000 cycles, there's got to be something wrong. Was the oven actually on? You know, you start to ask the questions. So on the right-hand side, you can see another example where you can see a very small micro crack. Again, at the same point in the corner, and just a little crack. Again, that is very unlikely to fail, and it certainly wouldn't change any of the electrical characteristics or the resistance of that particular via hole. But that's evidence that something has happened. So what you're trying to do when you do evaluations of any, you're trying to get a reference point of what's good and bad, what's better, and this is great because you can see the evidence. But please, if you don't prepare the microsections better or properly, then you won't get any information. And I'm not saying these are perfect, as I said, but they're a lot better than the first ones I was given. And these are just nicely highlighted by the yellow rings in those examples. Now, another little thing, and it's very practical, really. When you've got a microsection, you've finished, you've produced it, you obviously want to examine it. So the important thing with a microsection is it's got to be flat, because there is nothing worse than trying to use a high magnification microscope and having to focus on every single joint. So little trick, you just take a glass slide, which you see here, you put a little piece of plasticine underneath it, and then you apply a force onto the microsection face, and what that does is level it. So even though the microsection possibly isn't particularly level or parallel from side top to bottom, the plasticine just takes up that difference, and then you put that on the microsection table. You can go backwards and forwards with the same focus and not have to refocus for multiple photographs or measurements, etc. Just a little trick of the trade, and it just works so well. It's very boring having to realign and focus every single joint you're looking at. You might not have the time to do that. Now, I've mentioned about microsectioning and samples, etc. I just thought there was an opportunity to show a few other things that we could do, a few other techniques, and these are QFNs. Now, you can microsection in the traditional way, cut through the solder joints, etc. But there are other things you can do with a microsection or the potting of a microsection to help you understand and look at certain aspects of manufacture. So what I've done here is I've taken a sample. This has been through soldering, etc., but I'm actually microsectioning up through the board. So rather than going through the solder joint, I want to look at any corrosion or potential failures underneath the package without disturbing anything underneath the package. So basically, I pop the sample in epoxy, like you've seen. I'm using it as a handle to hold the sample, but it allows me to slowly grind down and grind down further until I'm literally at the back of the copper pads on the PCB. And by doing that and controlling the depth that I'm going to, it allows me to examine any failures that I might have had during contamination testing, SIR testing. So I'm not disturbing any of the failure mechanisms, but I'm being able to analyze it with a microsection. And I just show you a couple of examples, and these were done in using this technique. and you can see optically through the resin in line with the copper pads you can see here. And you see those little Christmas trees, and there is an X-ray version of it as well. So I put the microsection in an X-ray, and you can see dendrite formation. So if you were to take that package off, rip it off, rework it off with hot air or whatever, you destroy that information. But with using epoxy to hold the sample in place, again, you can use it in a different way to show up what's actually happening without losing the information. Because in failure analysis, the information is the most important thing, never destroying it if you possibly can. You can cut up the sample, but don't destroy the information if you can retain it. And certainly, you'd photograph it before any step in this operation. So here's another example. I'm doing exactly the same thing here. This is a module which was failing in the field. The thing was completely encapsulated in solid lump of plastic, but I still had to pot it to hold it. And again, I'm doing the same thing. And all those sort of light green areas are what I'm going closer and closer to try and see where the failure is or started to occur, or the change in resistance has started to occur. And you can see on the bottom right-hand side here where there is corrosion deposits within the package after operation in the field. And then again, another one, and you again see the Christmas trees growing in this particular example. So it's just using the technique in a slightly different way. In addition, I've used it for blind vias or buried vias as well. Now, these are examples of vias, and these are the back of the via. So the big square things are the pad that you've made your solder joints on. So imagine you're looking at the back of the pad with the solder joint on, but what we're interested in is the track which is connecting to the via that you can see that looks like 6 frying pans. And by doing this in the way I've described, potting the sample, grinding to the back through, and then stopping just before you get to the copper pads, I was able to examine the connection and the reliability of the connection between the pad and the back of the via hole. Because the back of the via hole is the thing that quite often can fail or not be plated correctly. So again, it's just a different technique again. I've got a paper specifically on that test if you're interested. So documentation, key thing, and a lot of companies don't do this very well, is when you're looking at boards or assemblies, you've got to document it, what you want from your supplier. Do you want it to level 2, level 1, level 3 of IPC? What materials do you want them to use? If it's a board that you're having assembled, you know, what solders are you going to use? What specification do you want? You've got to have some basic criteria, something in a contract to define what you want, because I or any other person looking and checking a board quality out for you, it's got no point of reference. Often I've been asked, well, is this board meet IPC? I say, well, what level of IPC? And designers quite often look at me very vaguely. I said, well, I can't tell you it's right or wrong until you tell me what you've paid for. And you don't want to embarrass yourself with your supplier if you get it wrong. So again, define what you want, very important. So you define the laminate you're going to use, the copper plate thickness, the solder mask thickness on the board. These are things which are important to define. And then, at least if you want to check them, or you want to check them because you've got a problem with your boards, you can again check them against the standard you've purchased your boards to. If you don't have that in place, then you will have a problem. Now, again, most design departments, design software come up with a build of materials or a build of boards, as you see here. And this shows you the build, the materials that are going to be used on the particular product. So I would use something like this as a point of reference if I was doing a microsection to check the build of the board. I would check the thickness, the number of layers, the positional accuracy of those layers, etc. You know, all that sort of stuff. I'm just checking what you told me should be there and within tolerance. And that's what, again, microsectioning is being used for quite often today. We're also looking at solder joints. And again, we look at the metallurgy of a solder joint. We look at the thickness of plating. We look at the intermetallic thickness. We look at the nickel, if it's a nickel gold board, if it's copper based board and it's been through a soldering process, how much copper has been removed during the soldering operation, all of these sort of things. And again, you will have on a microscope, what you should have, the method of measurement. And here you can see we've got a digital measurement which has been taken directly from the microsection. Very important to check the readings against your standard to make sure that you're actually reading what you think you're reading, because obviously if you use a different graticule on your microscope, then the numbers that you're reading may be inaccurate. If it's a manual system, if it's automated, then it shouldn't be an issue. But always check that the calibration of the system that you're using is right against something. Normally a glass standard, a glass master is the normal way of checking measurements out and comparing them. You also sometimes are presented with documentation from a PCB manufacturer, and this is just an example from some boards I had made, I think, for a project. So again, it would give you yes or no, or thicknesses based on IPC inspection criteria. So I might be asked to look at a board and see whether it actually is what has been represented here or not, or whether it exceeds or is worse than the samples being portrayed. Again, that information is normally provided with a batch of boards. Some people just throw it away. Some people keep it. It's entirely up to you. But that's the reference. The boards have been checked to the standard that you have requested. Like if you look here, it's to 6012 and it's level 2 of that. But if you haven't asked for level 2, if you've asked for level 3, then clearly they are not adequate for what you want. Just a couple of examples now of microsections and failures. This is a separation of an inner layer on a board. This is a multi-layer, and you can see the separation between the inner layer copper and the plated through hole. And that's an optical image that I've put a yellow circle round. And on the right-hand side, you can SEM, scanning electron microscope view of the same thing. So you can see this separation which has taken place. Now, whenever I do microsections of plated through holes, and you know you've seen a failure like the one I've just described, I normally section the board again because there is a benefit because you can see further information. So what I do is take a microsection. I've already gone through halfway through the hole, if you like, but I didn't have a drawing to show that, so I just show it with this. I take the section and then I microsection it through from the top or the bottom. And what this allows me to do is to see whether that defect that I've seen initially is representative of the rest of the plated through hole ring. So in this particular case, you can see here that on the left-hand side, that difference in appearance, that gap, is present in one plane, and it's not so obvious as you go round the hole. But on the right-hand side, you can see the separation on this example, where the inner layer copper, there is a definite gap all the way, or pretty much all the way around in the field of view of the photograph to the plated copper. So again, what we're trying to do is understand the type of defect, how widespread it is, how bad it is, as opposed to if it's just a simple issue that might well be met with IPC. If you look at IPC level 2, and certainly level 1, some separation between copper is acceptable, but the one on the right in this example clearly wouldn't be. So again, just a difference between specifications and criteria. Now, one of the other things that we do sometimes with samples is to do some stress. So if you take a sample, be it a PCB, an assembly, a solder joint, we may well stress it before doing microsectioning. And the idea is to show up what changes might have occurred. Is the sample possibly going to get worse by itself? It's not going to get better by itself, and how bad that might be. So in PCB fab, sandbath shock, thermal shock, or solder thermal shock is pretty much standard practice. So you take a board, you would put it and expose it to 260, 270, whatever the temperature you've agreed with your supplier for tin lead or lead free, and you're simulating what you are going to be doing in the soldering operation. And what you don't want to see is copper separation, copper separation from laminate. So you're doing this mechanically or thermally to try and show up variations in the quality of the product that you're testing. Again, this is all defined within the IPC standards or defined by you as a customer. So in this particular example, we've done thermal shock. There is a hairline crack, which hopefully you can just about make out on these slides. It's similar to some of the cracks I showed you earlier, but this has just gone through 6 thermal shocks at 260 degrees C. And this will maybe change the resistance value of the sample after testing. It depends on how you're assessing your samples. Personally, I don't think it's ever going to fail the board electrically, but again, it's may or may not be a failure depending on what your standard is. But it's just a nice example of what actually happens during thermal shock. In this example, you can just about see the separation of the copper from the laminate in this plated through hole. So we've got a nice solder joint, there's solder in there, but the copper has come away. So it's poor adhesion of the copper to the laminate. So yes, you could generate it if you're an assembler by exposing it to too long a heat, too many soldering operations, etc. But in my opinion, it's more likely to be an inherent problem with the PCB to start off with, the adhesion of the copper to the through hole. In the introduction of lead-free technology, when everybody was changing over to high TG laminates, there was a lot of this because the preparation of the epoxy prior to plating wasn't really done very well, and we got a lot of these instances of this happening, this separation taking place. Now, as I said, we can do microsectioning, and we can do microsectioning on very, very small holes and blind vias. And these are just a couple of examples. These are back in 2004 when I was doing testing on via holes with lead-free. And you can see here, these are gaps, small gaps between the via plating and the copper capture pad. Again, this is pretty typical. And in my opinion, nothing to be concerned about. In 2004, we were just able to use X-ray techniques to see the shape of vias. You couldn't detect cracks at that level, but you could see the shape of it. And the reason I show you this is just to show you the difference between a laser cut hole, which is the top example, and the bottom is the X-ray of the drilled or controlled depth drilled via on the left-hand side. So just shows you that there's certain things you can see, but of course X-ray moves on every 6 months, so the quality of X-ray and detecting cracks is a lot superior today. But just you can use different techniques to enhance what you're doing and looking at with a microsection. And in addition with microsectioning, of course, you can do other things. This is an example where I'm looking at a microsection of different soldering temperatures, different times with different materials, and looking at the characteristics. I'm then taking that sample, and then I can do analysis on that. So if I've got SEM with scanning capability, I can look at the difference in the distribution in this particular case of lead in the solder joints. You can see there's no lead in area 2 or 3, but there's still lead at the interface at where we're taking the spectra 1. in this example. So, there's lots of other things you can do with your microsections after you've actually prepared them. So finally, if you go to the YouTube channel, there's a whole video specifically on there about microsectioning and the benefits of microsectioning. It's not as long as this webinar, but that might be useful. And there's lots of other stuff on there which may hopefully be useful to you. So just before we take any questions, if you're interested in webinars, there are 3 more for the end of this year, 1 in October, 1 in November, and 1 in December. So 1 on PCB fab, 1 on hand soldering and desoldering, and 1 on conformal coating applications. And of course, we have our recorded webinars series, and we have also our on-demand webinar series. So in the on-demand series, we've got countless webinars that we can do for companies. If you need to train a group of staff and you want something on demand, you just tell us when you want it, what time you want it, and we'll present it. So all of these things are available to you if this is useful for you and your team. Okay, any questions? So during the session, if you've had any questions, they will be on my list, and I've got a few to start off with. So when you're doing vacuum, to remove gassing from microsections, what sort of pressure do you apply? Well, basically, when you buy a small vacuum pump, you can buy them specifically for this purpose. So they're calibrated just to pull a slight positive vacuum to remove excess air from your bell jar. It's normally in a bell jar. And what you're looking for is very, very slow emulation, very slow, the appearance of bubbles from the epoxy. If for any reason when you try and pull a vacuum and you have never used the equipment before and you see lots of bubbles coming out very quickly, turn off the pump, because the inside of the bell jar will be coated with the epoxy in your sample. Because if you get a lot of movement too quickly, that's what will happen. It's the same as when you're soldering in a vacuum. If you're doing reflow soldering in a vacuum, if you pull the vacuum too fast, the air is pushing the solder off the board plus the components and splattering it all the inside of the oven. So you're doing it as slowly as possible and just looking for those bubbles slowly coming up to the surface of the epoxy. So adjust the vacuum like that rather than just rely on me giving you a particular number. Next question. Do you have to wear gloves doing microsectioning? Well, that's a very practical example. I personally do, because I don't like the epoxy on my hands. It's not I've ever had a problem from a health and safety point of view. It's just I just don't like that feeling on my fingers. So I tend to always wear a pair of gloves whenever I'm doing microsectioning. I think it's good practice. And again, it doesn't protect you, because if you put your fingers too close to the grinding wheel, you can take the skin off your fingers, and even if you've got a pair of gloves on. So you just be careful in what you're doing. It's not a major issue. It's just experience, basically. Where can I get IPC standards? Well, pretty straightforward. IPC. If you go to the IPC website, if you're a member of IPC, or you're a corporate member, there will be 1 or 2 people in your company that get all the standards as they're released, new standards, and they get 1 copy. And that's part of the sort of contractual agreement. But if you want to buy them, you just go to the IPC store, or any IPC distributor or training company will be able to get standards for you. And obviously they range in price depending on the number of pretty pictures and the size of the document. Okay, so if there are any more questions, please type them directly into the control panel, and I'll do my best to answer them for you. Okay, that's a nice one. Somebody asking about microsectioning BGAs. Do I add epoxy before doing the final potting operation? It's interesting that sometimes what I do is, with some very small packages or very delicate packages, I sometimes do a double potting operation. I sometimes put epoxy onto the surface of the board, let it capillary underneath the sample, and let it cure. So I'm sticking the component to the board and I'm trapping everything. I'm making sure that nothing's going to move. And then what I would do is prepare the sample, cut the sample close to where I want to examine, and then pot it again. And all I'm trying to do is minimize the possibility of any damage, because if I damage the sample during the potting and cutting operation, then I'm going to give misleading information to my customer. So again, it's your own practical experience how you modify or change what you're actually going to be doing. But yeah, it's something that I do. But certainly, if like I said during the presentation, if I do something like a switch, something that's a mechanical device that I'm microsectioning through, there's always going to be cavities there. There's always going to be holes there. So sometimes what I would do is I would take a little drill. I will drill into the switch, and I will force epoxy in through the hole. I'd normally do 2 holes, so you can see the epoxy going in and coming out when it's full. Let it cure, then pot it for real before I actually do the grinding operation. It's because all the little bits come out of the switch, they go on the abrasive wheel or they go on the polishing cloth, and they damage your sample, and you have to sort of do a lot more work to recover it. So sometimes it just depends. There's always a just depends. Okay, any more questions? So I'll just give you a couple of moments of silence, and I'm sure you're looking forward to that, just to see if there's any more questions coming in. A reminder that I will be sending you a copy of all the slides, plus a copy of the charts that I mentioned at the start of the webinar. Okay, well, there doesn't appear to be any more questions coming in, so what I would do is say thank you very much for attending this webinar. Hopefully it's been interesting. As I said, you can see all the other webinars we have available. If you want one of those on demand for your company, that's absolutely no problem. All you need to do is go online and contact me, and I'll do my best to present them for you at a date and time that you require. So once again, thank you very much, and good afternoon to you all. Good afternoon.